So, what we do now is something which is related to the thermal properties of a magnetic insulator and this is an application which is actually quite relevant and important, and this uses a beautiful observation that I have been harping on for quite some time, which is that your this partition function, if you look at, is a function of h by kBt. Now, this I have mentioned several times in my previous lectures. Now, if you look at then you can calculate the entropy from it. So, the calculations that we did so far for Curie's law, for example, they are more or less followed by insulating crystals containing rare earth ions. These rare earths have deep lying 4f levels, which are incomplete unfilled shells, and then they have a moment, quite large moment, which shows up in this susceptibility measurements and magnetic and paramagnetic behavior, and corresponding 1 by T susceptibility. What is interesting is that if you look at your S is basically kb into beta square del f del beta. Okay. Which is basically minus del f del t. Remember this formula, of course, you remember that S is equal to negative derivative of free energy with respect to temperature, which if you write remember that kb beta is 1 by kb t, and then what you do is that this del f del t you can write as del f del beta del t, and you can see this del beta del t gives you this beta square term. Okay, so kb beta square. Now, the thing that one wants to do is have an interesting application out of the fact that your free energy, if you remember your previous view graphs, that remember this z. See, there z was always a function of h by kBt. So, let us see the other simpler one. So, if you calculate the partition function, it is just 2 cos hyperbolic mu b h by kBt for j equal to half. For j equal to large values of j, large any j, there are these other factors, but this formula is still more or less obeyed, except for some numerical numbers, additional numbers here. But the thing is that f is minus kBt log z. S is basically log of z times 1 by beta. So, that will do what? I mean, that will be just as I said here, but z is a function of h by t. So, f will be a function of just 1 by beta phi of beta h, some function of beta h. So, f is a function of beta a 1 by beta some function phi of h by t, or you can write it as 1 by beta as a function, since a functional relation is beta h. Okay. Kb being a constant, you can always do that. So, this is interesting, that fact that h is only a function of 1 by beta times a function of beta, a quantity which is a function of h by t. This is going to be used. Now, I can immediately do the derivative that I want to do to calculate the entropy. Okay. So, before I just do the calculations, let me just try to tell you what I am trying to do. This is the interesting observation that we have made so far, that your partition function is a function of is just a function of some function g of beta h, right. That means g of h by k t, h by t, some function of I can write it as g of h by t. Now, this this thing says that if I reduce my h, I have to necessarily reduce my t also. So, h by t is the factor that goes in. So, this is used as a, suppose I want to keep a quantity, suppose I want to keep z fixed and then I am reducing my h, then you have to reduce your t because it is a function of h by t. So, entropy, as I will show, is a quantity which can be kept constant in an adiabatic transformation, and so therefore, one can use the fact that this quantity is being a function of only h by t in the ratio, not individually h, not individually t. It is the ratio that appears always, that can therefore be used in an adiabatic process. If you go through an adiabatic process by keeping s fixed, and then actually you do it as I will show you, do it alternately adiabatic and isothermal, and therefore, you can reduce the temperature of a system whose entropy is dominantly coming from magnetic entropies. So, that is the thing that we are going to do, that is a practical application that is actually being done, and that is used, and so that is why it is a beautiful application from a simple observation of a mathematical form, that the partition function is a function of h by t, not singly h, not singly t. So, that is the pretext, I say the prelude to what I am going to do. Okay. So, let us now start doing the calculation. So, beta times f is phi of beta h. Okay. So, I take a, I do a, see I need this to calculate entropy, I need del f del beta, then I will multiply by k b into beta square. So, this will be, I will take derivative on both sides. So, this will be 1 plus f plus beta del f del beta equal to del phi del beta, which I write as phi prime. Okay. So, f plus beta del f del beta equal to phi prime. I have to multiply it by k b into beta square, remember. So, it is here on the left hand side, you can see I have to multiply it by k b into beta square to get my entropy. K b into beta square into f plus beta del f del beta equal to k b beta square phi prime. Okay. So, k b beta square del f del beta. So, from this I find out k b beta square del f del beta. Okay, so, I do not multiply by, I multiply only by k b beta, therefore, I have this. So, this will give me immediately k b beta square del f del beta, and that is then equal to minus k b beta f plus K B beta phi prime. Now, f is 1 by beta so that will cancel my beta here, and so the result that I will get is K B into minus phi beta h. So, I am using the fact that f is equal to 1 by beta phi of beta h. So, then this gives me plus beta h phi prime. Remember this phi prime there, sorry, there was a h sitting there because I took a derivative with respect to beta. Sorry. So, this is correct, but there is a h sitting here. See, this was beta h. So, I took a derivative with respect to beta. So, h will come out and that is this beta h phi prime. Okay. So, this is my S. Okay. So, that is the expression written on the left hand side. Entropy has this formula that K B into minus phi beta h plus beta h phi prime. Okay. Again the same statement that S depends only on this quantity, S depends only on beta h, which is h by t, right. So, suppose you want to keep S fixed, which is basically what you do in adiabatic changes, then you you can lower your field. If you lower your field, then you have to lower your temperature, because your S is fixed, and this is the ratio by which phi depends on both H and T. So, that means if you can adiabatically decrease your field, then you can decrease your temperature. See, these are of course the technical the things that you have to keep fixed. As a result, by adiabatically, that is at fixed S, lowering the field acting on a spin system. By adiabatically one means slowly enough, so that thermal equilibrium is always maintained. One can lower the temperature of a spin system by the proportionate amount. I mean, that is exactly what I have been saying. So, you can write then that suppose I have a T, I am going through suppose I started with an H initial and I landed up with H final. From initial to final I went. So, then this will just be equal to the same as T initial, right. This ratio has to be maintained because S is kept fixed. Okay. So, that means that T f is T I into H f by H I, f and I are final and initial. So, this is so if you reduce your H f, your T final has to reduce. And this is how it is actually done. So, this picture is already quite nice. So, let me just follow this picture. What one does here is that one this is the entropy versus temperature plot. You have several curves for S for example. Remember the simple theory that we have been doing tells us that if you keep your H equal to 0, then of course there is no temperature dependence at all. So, that is a dangerous thing, because that will violate the third law of thermodynamics. But anyway, so let us that means that theory, that simple minded calculation that we are doing, that it depends only on beta h, has to give in give away has to give away at some point, and at very low fields or very low temperatures. So, it is actually at very low temperatures, this is not correct, but let us just remind you that there is this pitfall, that this theory predicts that at h equal to 0 you have a completely flat curve, no dependence on temperature. We will come back to it, we will discuss it. Now, so the actual h is like this at h equal to 0, actual s at h equal to 0, and then of course, this for higher values of h, this side, it is c to b, the value of h increases. So, what you do is that see, remember the dashed line represents the constant n k b log 2 j plus 1, that is what I was saying, that you have no dependence on temperature, and 2 j plus 1 is the degeneracy of the jth level. So, that is that was the entropy at very high temperature, that is correct. That is what you see, all these curves at very high temperature go to this n k b 2 j plus 1 log 2 j plus 1 value. Anyway, so the process here is that you start from point A, cooling cycle is at A with T I and H equal to 0, then proceed isothermally to a point B. Okay. So, this is the point B, you come down isothermally. So, entropy is reducing here okay. So, this is from A point, which is h equal to 0, to B point, remember, is h has increased. Okay. The next step is to remove the field adiabatically. So, we come from A to B by raising the field isothermally, then adiabatically we now start reducing the field and go from say B to C, which is again h equal to 0, the actual curve, but you can stop at h2 or somewhere, but basically you reduce your field. So, you come along this way, but adiabatically, which means your entropy is constant, and then you see what has happened. Your temperature here was T I, the temperature here is T F. So, you have actually managed to reduce your temperature of the system by this process. So, you start from a very low field, come to a higher field isothermally, and then go to a lower field adiabatically, and this process can then be, then this point C becomes your initial point, and then you keep on doing the same process, isothermally go down, then adiabatically go to the left, and by this process you can repeatedly applying this process, you can reduce the temperature of the system. Now, of course, this is a beautiful scheme, but as I said that this kind of simple theory really does not work, and it breaks down at some point. So, where does it and why does it break down? It breaks down simply because the fact is that it cannot be that the spins spins only depend on the entropy only depends on the moments, right. In a real system, that is not going to happen. Of course, at very low temperatures, the contribution from spin moment to the entropy is probably large in an insulator, and the phonon contribution there is small. But then they remember that this also says that at h equal to 0, if you have h equal to 0, then you have no T dependence, that will violate third law of thermodynamics. So, at some point, definitely at a lower temperature, at some temperature somewhere, this theory breaks down, and this you have to consider this the other effects that come in, particularly the effects at low temperature, which are very important, are these moments start talking to each other, and because there is no other effect, thermal effect is small, and other energy scales have already been very small. This is this interaction energy between spins of between moments of different ions, or between different moments basically, are not negligible anymore, and that will restore the physical law that S has to go to 0 at t going to 0. And but then of course, this is used. So, this is used in certain materials which some insulating materials containing the rare earths and paramagnetic salts, and there of course, it works to take your temperature. You start at a temperature which is around few degrees, and then it can take you down to about a 1/100th of a degree Kelvin and so on. Below that, of course, it will not work, but this reduction by a factor of 100 can be achieved using adiabatic this is called the adiabatic demagnetization procedure, by which you can reduce the temperature, and it is a cooling, basically it is a procedure for cooling refrigeration, and it is interestingly it is more or less pollution free, because nowadays that is a very important issue, because you are using not burning any fuel or not spending too much of electricity and so on. So, you are using a magnetic cycle to do it. Of course, to do the magnetic cycle you need some energy, but turns out it is a very safe and nice method to go down in temperature. But as I said, it has its limits, and it stops working below a certain temperature. So, if you want to use it, be careful and choose your material very carefully, whose magnetic cycle you will be using, and then of course, your of course, you use a magnetic insulator, but even then you will not be able to go down to extremely low temperatures. For that, there are other methods which we will not discuss here. So, basically this is an application of thermodynamics of a magnetic system, and what have we used? That is a very simple mathematical observation, and which is actually guided by physics, as I have been discussing, that if you want to raise H and also T, then these two actually oppose each other, and therefore your partition function, for example, will reflect that fact, that your magnetization will reflect that fact, that your magnetic for example, these kind of magnetization, for example, is a function of only y, and because obviously the magnetization has to decrease as you increase temperature. Magnetization has to order, become larger, magnetic moments have to order, magnetization becomes larger if you put more field. So, this H divided by T is the common ratio that dictates the play of field and temperature, and if that is true, then of course, if you keep a quantity like entropy which depends only on this H by T fixed, then by changing H you can change T, and this is a beautiful way of very nice way, cute way of using a mathematical fact or a physical fact to lower the temperature. Of course, in every method you use a physical fact, but this is a magnetic system, and by using, you do not associate magnets with refrigeration, right, but here for example, a magnetic interaction, magnetic phenomenon, that simple thermalization and ordering, these two opposing processes, they appear in the ratio, and therefore that can be used to a clever way, in a clever way, to give you this cooling refrigeration. It's a beautiful way to do apply a physical phenomenon which is unrelated normally to another field of science, which is a technology here where you want to go down in temperature, cooling, and so this is a complete subject of cryogenics that people study to do these kind of things, and this is one of the methods of cooling down from few degrees down to about 1/100th or so of a degree by using certain paramagnetic salts, insulating paramagnetic salts. So, next what we will do is that we will go to another interesting phenomenon which in the next class I will discuss.